were all between the orbit of Mars and Jupiter, and they were all really, really small. And so after a while, when there was 35, 40 planets, they said, wait a minute, we got to do something here. Because Neptune was discovered, and Neptune was a big planet, like Uranus. And so they said, you know what? We're going to just call these something else. We're not going to call them planets. We're calling them minor planets, asteroids, everything between Mars and Jupiter. That's a small thing. We call them asteroids. And at that point, we were down to 8 planets. Okay? That's where we were. And then Pluto was discovered in 1930. And there it was. And we have the 9 planets. How many of you learned in school that we have 9 planets in the solar system? All right, everybody learned that in school, except what happened is we discovered Pluto is not alone. Pluto has so many friends and relations out there. I looked it up yesterday just so I could give you a count, and there's at least 22 objects out there near Pluto that by Pluto's standard would be considered planets. All the ones that I have named there, Makemake, Quaoar, Sedna, Orcus, etc., those would all be planets by the definition of making Pluto a planet. So we decided to make them all Kuiper Belt objects, just like we did with the asteroids. And now we're back to 8 planets. That's where we stand today. I wanted to give you that tutorial because this is how science progresses, right? You find new things. You have to categorize them in ways that make sense to you as a scientist. Okay, so let's talk about exoplanets. Even before Pluto was demoted in 2006, the age of exoplanets had begun. The first exoplanets were very strange. In 1992, exoplanets were found circling a pulsar, which is a really highly energetic star that spins really fast. And people were measuring the chip, 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 chip of the spinning, and they discovered it was slowing down and being modulated by planets. And so that's how they found out there were planets around that star. But more normal planets were found in 1995 around a star, which is like ours, 51 Pegasi b. And they were looking at the position of the star, and it wobbled back and forth. And based on the wobbling, which is shown here, the blue line is if there's no planet, it would not wobble. But it was moving up and down in this plot, and that told them there was a planet there. So this wobbling was, for a while, one of the most important techniques to finding planets. The discoveries were pouring in, just like with asteroids, just like with Kuiper Belt objects. Every year, first there's 1, then there's new, then there's 10, then there's 100. And so just more and more planets are being discovered all the time. The powerhouse for finding planets is a technique called transits. And it's illustrated in this chart. You look at a star, and when a planet crosses in front of it, the starlight dips. It gets fainter when the planet's blocking out the starlight. If you have a little planet, it's a little dip. If you have a big planet, it's a big dip. So by looking at these transits, that's how we're building up our knowledge of what planets are out there, how big they are, what their orbits are. And the king of this was a telescope that you may not have heard of, the Kepler Space Telescope. How many of you have heard of that? A few. This is a good audience, very well educated in astronomy. Kepler had one job. Kepler stared at a piece of sky for years, just one tiny piece of sky, looking at every star in that piece of sky, 115,000 stars. And it just watched the stars looking for dips. And this plot here shows you different sized planets that were discovered by Kepler. So many planets. To give you an up-to-date, I went to the Exoplanet website at the Jet Propulsion Laboratory today. This is their dashboard today. As of today, there are 5,747 confirmed planets around other stars. So another factoid for you to remember, in addition to ice giants are special and unique, is that there's over 5,000 planets that we know of that are confirmed out there. And this chart shows you the yellow ones were found by transits, and the blue ones were found via the wobbles that I talked about. And there are other techniques that I'm not going to go into today that show you that there are other kinds of planets. Now I'm going to show you like the one takeaway chart that probably the most intriguing thing that I'm going to tell you today. And it's taking these planets, these 5,000 planets, and plotting them as a function of their size. So when we look at Earth-sized planets, about 600 of them known today. And when we look at Neptunes, there's over 1,600, of 1,600. Jupiter's not quite as many really big planets, even less. But this bar here, this bar is a bar we call the sub-Neptunes or the super-Earths. That is the most populous kind of planet in our galactic neighborhood, and we don't have any of them in our solar system. So we cannot study in detail the super-Earths or the sub-Neptunes. All we can study is Earth and the terrestrial planets, or the Neptune and the Uranus, and try to infer what is in between. And so to truly get ground truth for these most populous class of exoplanets, we need to study our Neptune and Uranus objects in our solar system. And so that is the reason they are so important to us. The problem is that they're very hard to study, really hard to study. And I'm going to talk about Uranus first. And the reason I'm going to talk about Uranus first is because it's the easier of the two, because it's closer to us. But close is a relative thing. Here's an artist's concept of what the sun looks like from Uranus. That brightish star back there is the sun. And here's what it looks like from one of the moons of Neptune. That little tiny thing up at the top is what the sun looks like from Neptune. These planets are so far away that you require the biggest and best telescopes in the world just to see anything on them. Now, there are small telescopes that give you hints of stuff, but to really make progress, you either need to send a spacecraft mission or you need to use the biggest telescopes in the world. And let's talk about how many missions have explored these planets. This is a chart of all the missions that have explored everything. Lots and lots of missions all throughout the solar system until you come to Uranus and Neptune. And there's been exactly one mission that has flown by Uranus and then flown by Neptune. That's Voyager 2. And that one happened in 1986, and the other happened in 1989. And Julianne mentioned that I was very honored and lucky to be a grad student at the Voyager 2 Uranus encounter. As a grad student, your job is to get coffee for the scientists and get the printer, printouts off the paper and deliver them to the scientists. For Neptune, I was one of the scientists. I had finished my PhD, which had been studying the Neptune clouds, and so I got to actually be there. But I was there for Uranus as well. So I like the next picture. We always pick the best picture from the system to put on the cover of Science magazine. The next picture I'm going to show you is the picture of Uranus they chose for the cover of Science magazine. That's it. Very dramatic. The reason they picked this picture of Uranus is because to Voyager, that's what Uranus looked like. They saw almost no clouds. If you really stretched hard, you could pick out 10 cloud features, 10. One for each finger and thumb. That's it. That's all Uranus had going on. And everyone's like, oh my gosh, it's such a boring planet. It must be because it's so far from the sun. Actually, it might have something to do with its orbit, but it's not a boring planet. So here's a telescope that I use. This is the Keck telescope. It's a 10-meter segmented telescope. To see the person in red inside the telescope, that gives you a sense of scale of how big it is. And what you can do with the Keck telescope is something called adaptive optics. And adaptive optics allows you to take out the twinkle of starlight, the smearing of the Earth's atmosphere. And so here's a picture of Uranus that I and my colleagues took with the adaptive optics turned off, and it kind of looks like your Voyager picture. Maybe there's something bright going on one side, but when you turn the adaptive optics on and remove the smearing of Earth's atmosphere, this is what Uranus looks like in a 10-meter telescope. And you can actually, in this one image, start counting spots. These are cloud features in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's more cloud features in this one single Keck image than in all of the Voyager images. You can actually even see the ring of Uranus. You see there's like a line going across there, slightly different angle. So very, very interesting. And we were able to use this to do lots of fabulous science studying the atmosphere of this planet. Why did Voyager see nothing, and why do we see clouds? Hubble actually saw clouds too. We think it has something to do with the year. Now, Uranus is the planet that rolls around the solar system. It's tilted over 90 degrees, and so its rotation axis is sideways. And when Voyager flew by, it just happened to be at the solstice, where the pole was pointing at the sun. So no matter how it would spin, one hemisphere was lit up and the other hemisphere was dark. And the atmosphere looked like it was turned off. But that's Voyager. But as Uranus went around its orbit and more of the planets started getting sunlight, clouds started to pop up. The equinox was in 2007. We had a huge observing campaign, all kinds of cloud features and cloud structure. We are now moving past that, heading towards the other solstice. It's going to be interesting to see if the atmosphere turns off again. We don't know, because we haven't been able to observe with the kinds of tools you need, so we don't know, but it'll be interesting to see. So here's a compilation of Hubble images showing you sort of this changing geometry. And I like to compare it to this sketch of Uranus that was made in 1915. Back in 1915, people looked with their eyes, and they could pick out moments of clear seeing, and at that time, they saw the structure that we now see with adaptive optics. So we're now kind of getting to the point where our technology is almost as good as the human eye can do. Human eye-brain combination. Okay, so I like to show you this because these are the best maps of Uranus ever made. This is Uranus. And we got these with the Keck telescope, and we did a lot of processing, but you can see all kinds of interesting structure. We have observed since then, but the images are not better because this was working at the edge of what this telescope could do. So we have lots of comparably good images. This was the first of this nature. And I like to show structure like you look along the equator here, you see all kinds of braided structure. That's a wave structure at the equator. If you look at the polar regions, we see all sorts of weird, what we call popcorn clouds. We see stuff like this we saw it with the Cassini spacecraft on Saturn. This is the first time we had seen it on an ice giant. And we see what we call moist convective clouds. These are thunderstorms that well up, and in the period of a day, they subside, just like giant thunderstorms here on Earth. So very dynamic and very changeable. Don't ever fall for the line that Uranus is a boring planet, because it's not. Now that we have the tools, we can see how interesting and dynamic it truly is. Now, we already mentioned the James Webb Space Telescope. I worked on this mission because I wanted to see Uranus and Neptune. That was why I signed up in 2002 to be a scientist for this mission. And so that was our first glimpse of Uranus. Look at all the beautiful galaxies that you can see. That's what most people wanted to see with JWST, but I wanted to see this. This is Uranus and its ring system. And all those bright blue spots there, those are not stars. Those are the moons of Uranus. We can label them all, track them all. So really fabulous work that we can do with JWST. Here's a picture taken, two pictures with JWST taken exactly 1 year apart. February 6, 2003 and February 6, 2023 and 2024. And you could just see, you just look at the picture. You don't need to be a rocket scientist to say, looks like Uranus has changed a little bit, doesn't it? There's a whole lot more cloud activity in 2024 than there was in 2023. And we use this cloud activity to do things like measure wind speeds, measure heights in the atmosphere. JWST is great for that kind of stuff. But JWST has a superpower, and its superpower is the word spectroscopy. How many of you know what that is? A few, okay. We're going to have super fast tutorial on spectroscopy because you got to understand this for JWST. Isaac Newton put a prism in a pinhole, spread out the light into what we call the electromagnetic spectrum. What we see with our eyes, visible light. But there's light at all the other wavelengths as well. And you know these names, radio, microwave, X-rays, you've heard of that kind of light. We study all of this light with all of our telescopes. Hubble is awesome because it's visible. JWST is infrared. But more importantly than just the light itself is a characteristic of light and molecules and atoms. And that is spectroscopy. Some materials will actually absorb wavelengths of light characteristically. It has to do with quantum mechanics, and I'm not going to go into it today. Trust me, it works. Other materials sometimes emit light, depending on their temperature, the pressure, the light source, things like that. And so by looking at these lines of emission or absorption, we can learn about the materials out there in outer space, even though we can't touch them or be there. Now, in the early days, when I was a student and still today, we didn't have color printers. We couldn't make pictures like this. So what we did is we just drew lines. And when it was absorbing, it went down. And when it was emitting, it went up. And so this is called a spectrum. And for years, NASA refused to let us even show these. They called them squiggly line plots. We weren't allowed to show squiggly line plots, but we've actually been able to change that because it's so important. Here's an example. Here's a star exploding. Cool. It's a beautiful image. Astronomers look at it and go, yeah, but what's the spectrum look like? And that's what the spectrum looks like. And you can see helium and iron and nickel. And by looking at the shapes of these distortions, you can learn about dynamics. You can learn about the pressures, the temperatures, the chemistry. That's the science, people. That's what astronomers really get geeked out about, is the spectroscopy. So let me now show you what a spectrum of Uranus with JWST looks like. All of this stuff that looks like noise and squiggles, that is chemistry. That's ethane, acetylene, it's methane. Even here, it's water, deuterated methane. Just incredible richness of chemistry that we can use to study the atmosphere. And more importantly, JWST can do images at each of these wavelengths. And so we can discover where the methane is on Uranus in a ring. We can discover that the ethane is actually only on one side in these images. The hydrogen quadrupoles are emitting all around the edge. So this is how we can actually do science and probe the structures of these things using the spectroscopy. Now I'm going to talk a little bit about Neptune's appearance. Voyager, we didn't need to play games. We didn't need to show you crescents because Voyager was so beautiful right away, dominated by a great dark spot right in the middle there. My first formal Neptune program with JWST was the same year as Shoemaker-Levy 9. And my big discovery was that there was no great dark spot. It was gone. It had disappeared in just 5 years, from 1989 to 1994. In fact, there was a new dark spot up in the northern hemisphere, hard to see in this picture, but that was like my big, like, woo, Hubble Space Telescope, incredible. There were no dark spots for a long time. Many years went by. I kept looking at Neptune, no dark spots. But back in 2015, a new dark spot appeared in the same general location as the Voyager Great Dark Spot. And it was changing with time, very dynamic, super interesting. But it didn't last very long. It only lasted a couple years. And then we saw a brand new dark spot up in the northern hemisphere, and there was a second one. There were two. So this is like changing its spots all the time. And why is that? We don't know. One of my colleagues at MIT, Tim Dowling, I remember the day that I had first gotten my Hubble data that showed no dark spot. He modeled dark spots for Neptune. That's what he did, right? He came into my office, said, Heidi, my model finally creates a great dark spot. And I'm like, I got bad news for you, buddy. And his models never could make them go away to this day. Once you form a spot, it's long-lived. Like Jupiter's Great Red Spot, it's still there. It changes shape, but it's still there. Neptune spots, they're there, and then they're gone. 4 years later, they're gone. And then a new one comes, and then it's gone too. We don't know why. All right, so we did look at Neptune with JWST. This is the picture that made me cry when I saw it, because I had been waiting for 25 years for that picture, and it was so beautiful. You can see the rings, you can see clouds, but I'm going to show you a science movie now. Just like I showed you different wavelengths of Uranus, like I showed you how it changed with wavelength, I'm going to show you a spectrum of Neptune, and then I'm going to slide through the spectrum and show you the pictures at all the different wavelengths of light, so you can see how Neptune's appearance changes. And here we are sliding through the wavelengths of light, and there's the Neptune pictures. And you can see sometimes there's big bright spots near the center, other times it's near the pole, sometimes there's bands at the equator. What's happening here is you're probing different altitudes in the atmosphere, and you're probing different chemistry in the atmosphere as you cycle through this. And so by taking all these images and mixing them together, we're starting to build up a picture of the three-dimensional structure of Neptune's atmosphere that we could not do until we had the James Webb Space Telescope. Something else about Neptune. I'm going to show you a whole lot of pictures of Neptune, and what I want you to take away from all these pictures is that there's a lot going on this planet. Until you get to recently. And all of a sudden, like, where did it all go? There's a lot of dialogue about this right now, and something very interesting. It seems that this cloud cover, how many clouds there are, seems to be linked to the sun, which is nuts. Do you remember the picture I showed you of how far away the sun is? How could the sun be changing these clouds? But here's a picture from a very recent paper by Michael Roman in 2024. I'm a co-author on this paper. And these little half circles here are what we call the filling factor of clouds, like how much cloudiness there is on the planet. So that's what that is. And you see it's going up and then going down. And the really faint line in the background, you see the faint thing? That's the sun. That's the sun's variability here. That's how much brightness is coming out of the sun. So when the sun gets brighter, there's more clouds. When the sun gets fainter, there's less clouds. Look at the time scales here. We're talking decades. And so you really need these super long time scales to pull this out. It's very intriguing. And we don't understand how this can be. We don't understand if it's the brightness itself that's driving chemistry, that's making new clouds. It could be something else. It could be that the changing magnetic field throughout the solar cycle is changing how many high energetic particles are coming in. That could be changing how many clouds there are too. We don't really know. So it's really interesting and fascinating. Now I'm going to geek out for a little bit. I wanted to give you some hardcore science for those who came for the science. We track the clouds, and that's how we get the wind speeds. So these two charts are the wind speeds of Neptune and Uranus. And we have prograde mid-latitude jets. We have a retrograde equator. The equator is slower than the rest of the planet. But if you look at the difference from 300 to minus 300, that's a delta of 600 meters per second. And that is the fastest wind in the solar system. So maybe all the clouds you're seeing are related to the super fast winds. It's not quite as pronounced on Uranus, but it's still pretty fast. So this is, supersonic flow. How can you have supersonic flow in an atmosphere? What's going on there? One of the speculations is that because it is so far from the sun and so cold, you have effectively frictionless flow in the atmosphere. And that's how it can go so fast. Now, when I said how cold can it go, these are some temperature plots as a function of altitude in the atmosphere. These are temperature in Kelvin. If you don't think in Kelvin, and I typically don't either, let me put Earth on here. At the surface pressure here in the room, which is 1 bar, the average temperature of the Earth is 300 Kelvin. That's 80 degrees Fahrenheit. Okay? So over here, this is the cloud tops of Neptune. They happen to also be at 1 bar, the same pressure as in this room, but the temperature here is 70 Kelvin, minus 333 degrees Fahrenheit. So extremely, extremely cold. Both Uranus and Neptune are cold. One of the things that's a little bit of a puzzle here is you look at Jupiter and Saturn and Uranus, and you would expect Neptune to be out here, wouldn't you, right? But it isn't. Neptune is actually the same temperature as Uranus, and it's even warmer than Uranus in its upper stratosphere. Why? Say it with me. We don't know. We don't know. We are hoping to learn that with those JWST data that I was showing you earlier, but we just don't know. And what are these clouds anyway? You know what the clouds on Earth are, right? You do. So the clouds on Earth are made of water, exactly. But that's because they're warm. Out here where it's cold, we actually have methane clouds at the 1 bar level. And if you could take away all the clouds that are made of methane, you would have another cloud deck. And that cloud deck would be hydrogen sulfide clouds. And then underneath that is another ammonia-rich ammonia sulfate clouds. And under that is the water clouds, because it got warmer as you went deeper in the atmosphere. And if you took away all those clouds, you would have more clouds. It's clouds all the way down. There's no surface. You could not land on this planet. It's just got clouds that get thicker and thicker as you go down. Now, that's a simplified picture called the standard picture. What we know in reality from all our data is it's much more complicated than that. We have this moist convection that I talked about, and we have these dark spots that seem to be reaching deep in the atmosphere. So there's some stirring that goes on. But the details, we don't know. We don't know the details. We need a mission to figure that out. I talked about the interiors a little bit. I just wanted to show some recent models of the interiors. We know there's an atmosphere. We know there's a mantle. We know there's a core. But what we don't know is the phase transitions. And you see the 4 possibilities are hard transitions, or maybe the mantle core has a soft transition, or maybe there's a gradual transition from the atmosphere to the mantle, or maybe all of them are, smooth transitions without sharp boundaries. And of course, you know what my answer is, like, we don't know which of these 4 possibilities is. You must have an orbiting spacecraft to learn that. And so that's why we want an orbiting spacecraft. Okay, 1 minute on the colors. Those of you who have been following news about the ice giants probably heard about this kerfuffle about the colors. These were the colors from the earlier Voyager images, all right? This is what we released from JPL, and you can ask me why during the Q&A, but this is not really very right. It's close, close. This is completely wrong. Absolutely, totally, completely wrong. We just did some studies where we rebuilt the colors with new data. This is what the colors look like. And I know it's not satisfying to have it look like this. You want it to be azure with strong contrast, but people, that's just not the way the planet looks. If we were there in a spacecraft, that's what it would look like today. Okay, now speaking of spacecraft, wouldn't it be nice to send a mission there? This is what Voyager 2 saw, and people say to me a lot, well, we've already sent the spacecraft there. Why do you need to go again, And my answer is, they've been there, done that. And my answer is, well, we did that with a spacecraft that launched in 1977. So let me show you some other things that launched in 1977. That was the state-of-the-art computer. Here's the state-of-the-art gaming, 1977. Wouldn't you much rather be, 47 years later? Wouldn't you want to have one of these? Wouldn't you want to have one of those? I know my son would like to have one of those, right? So that's the difference in technology that we are talking about here. We really want to go back. I want to go back. And if I had to make a mixtape, this is what it would look like. I want to go back, I want to go back, I want to go back. It's just we want to go back. How do we make that happen? And besides, everything we know about these planets has changed. I hope I've convinced you at least about the atmosphere, that's changed. But the ring structure has changed as well. That's a whole other talk. The satellite compositions have changed. That's a whole other talk too. And basically everything that we know about them from the Voyager system has changed. That's why we want to go back. But why are they changing? We don't know. We can't see the details. It's too far away. We don't have the right technology. So we really need to go back. So the way we do this in our field, and Julianne and I we work on these kinds of things. We write things called decadal surveys. Every 10 years, we write an assessment of what we have learned and what we need to learn. And this one, I was the chair of the Giant Planets panel. And so you will not be surprised to see that Uranus orbiter and probe was on the list because I'm a strong advocate. But number one was a Mars Astrobiology Explorer Cacher, which is now what we call Mars Sample Return. You can ask me about in the Q&A about that. And also, the number two was Jupiter Europa Orbiter, which is now the Europa Clipper mission, which is going to launch next month. So we get that one out of the way. We get that Mars Sample Return out of the way, and guess what? We got Neptune. We got Uranus Orbiter. 10 years later, there was another decadal survey. I was not involved in this one. I just watched from the sidelines. Their number one recommendation for a new large mission is they prioritize the Uranus orbiter and probe as the highest priority new flagship mission to initiate in this decade that we're in right now. We still have to deal with Mars Sample Return, though, because we can't launch this, we can't even start this mission until we've solved that problem. So that's the tragedy of my life right now. But, you know, I started working on JWST because back in the 1990s, there was no Neptune mission, there was no Uranus mission. And so what am I working on now? I'm working on the next big telescope, because that's what we got. It's something that we're calling Habitable Worlds Observatory. And Habitable Worlds Observatory maybe a launch date of 2039, maybe. What do you think, Julianne? Maybe. We don't know. We thought JWST would launch in 2011 when I started it. When it launched in 2021. Okay. This is actually being designed not for Uranus and Neptune, of course, just like JWST wasn't either. This is being designed to look for habitable worlds. And how many you can find depends on the aperture of the telescope. So for a telescope like JWST, that's the sample size that we get to characterize atmospheres. That's a 6.5 meter telescope. If you want to sample this, you need a 12 meter telescope. When ultimately, habitable worlds will likely be somewhere in between those, but it's going to do fabulous exoplanet science. There's a comparison of the mirror sizes of Hubble, JWST, and Habitable Worlds Observatory, big version, which is what I want. But what about Neptune? Remember I showed you this picture of Hubble? When I go from a 2 meter to a 10 meter, I'm going to show you a simulated image of what the Habitable Worlds Observatory could do for Neptune. Look at that, people. Looks just like Voyager, right? That's what I want. That's why I'm working on Habitable Worlds Observatory, and also for the rest of the community as well. So there's a lot of great science to be done. But it takes a long time to create these missions, whether it's, you know, the Uranus orbiter mission, 2039, 2040. Whenever we did trajectories, we were like, it takes 10 years to build it, takes 10 years to fly there. We would do the math, and like, when do we arrive there? It's like 2080. I'm like, how am I going to be then? You know, but you know, from the science perspective, that's okay. Uranus's year is 84 Earth years. Neptune's year is 165 Earth years. So it's a multi-generational thing to study these planets, to really truly study how they change with time, how the seasons vary on Uranus or on Neptune. It isn't going to be me. It's going to be kids or their grandkids or great-grandchildren. And you have to think in that perspective. That's how we do this for these big missions. And I just wanted to end just showing you the example from my own personal life. This is a picture of me in 2002. And that was the year I wrote the proposal to become a scientist for what was then called the Next Generation Space Telescope, but it is now the James Webb Space Telescope. And the next picture is this picture of me with the same baby when we got our first data from JWST in 2022, and there he is. All right? He's here in the front row. You want to stand up, show him how tall you are? Come on, just tall. It's my son. Yeah, good job. Yeah. So it's generational, I'm telling you. And that's when we got our first data. So 2042. I'm not going to show you a picture of what I'm going to look like then. I don't know. He'll be a strapping man at that point, but I don't know about me. But what I'm hoping is that we have pictures like this whether it's from missions to Neptune or Uranus, or whether it's from this advanced space telescope. I don't know, I just want it to happen. And so that's what I'm here to do, is to work to make it happen. So here's my takeaway messages for you from today's talk. Uranus and Neptune in the age of exoplanets. Uranus and Neptune are fascinating, dynamic worlds. They are not static, they're really variable. And I want you to take away that ice giant science is important and exciting because of advances like adaptive optics and the James Webb Space Telescope, maybe someday a mission. Understanding ice giants is going to be key for understanding the sub-Neptunes. Right now, all of our other exoplanets are points of light. And to understand their atmospheres and the dynamics and the variability, we are going to have ground truth in our solar system from our Neptunes and our Earths. Otherwise, it's just models. And bless all of you who do models, including Julianne. But models, you can make the models do pretty much anything. You can only constrain the models with data. And so that's why Uranus and Neptune are so important. They're the only data we have to constrain that edge of the exoplanet characterization. And finally, new missions, whether it's a spacecraft to the ice giants or an advanced space telescope like Habitable Worlds Observatory, they're absolutely required to understand these enigmatic worlds, which I love so much. So thank you. I'm happy to take questions. Are you going to be the questioner?
Great. Thank you very much, Heidi. That was just absolutely lovely. I just want to say, because I now figured out I cut off our special little intro.
Movie.
That's why, yes. Wow. So I'm going to try to convey the information. First of all, if there's a fire in the past hour, you can leave by the exits. But the other important bit of information is that you can't have any food or drink here in the last hour. But most important to know is that you have a button right by your seat that says speak. Some of you may have leaned on it and actually are turning it on, and we're hearing everything you say. So if you have a question, please make sure that your microphone is lit before we start questions. So.
Closest one.
So the question is, can we observe sub-Neptunes directly? How close is I don't know how close the closest one is, but we cannot image them. We see them as points of light, even with the biggest telescopes that we're designing. Even with the Habitable Worlds Observatory, they will be points of light. They will not be spatially resolved. So we will be able to, if they vary with time, from varying brightness, we might be able to pull that out. But we will not resolve them. Any pictures you've seen of resolved exoplanets have been artist concepts. There are no resolved exoplanets at all. All of them are points of light. I will share that at Aura, we're already thinking about what do we need to build to actually resolve an exoplanet. And you're not going to do it with a large single telescope. You need to use a technique called interferometry, which they do in the radio, but you take two telescopes that are separated and you combine the light from them in such a way that it acts like the telescope that has the diameter of those two. But here's the trick. To actually do this on an exoplanet, particularly an Earth-like exoplanet around a sun-like star, the distances need to be hundreds of kilometers. So no current optical interferometry has that capability. So what we're investigating is whether we can use the concept of quantum entanglement to take two telescopes that are hundreds of miles apart and connect the two of them by the properties of the light that is coming and look at quantum entanglement, one here, and then combine them. It's like crazy stuff. But the folks who actually study quantum are like, you mean we could actually do an experiment and build something, and it would do a thing, like image a planet, and they're so excited about it. So it is pie in the sky. I don't know if you've even heard about this concept.
No, I have not.
No, all right, but we're starting to do the groundwork now. So yeah, wouldn't that be something?
I also do want to say that will not have images of the resolved images of the exoplanets, but we will have spectroscopy.
Yeah.
Like that.
Absolutely,
This is where the
yeah,
information is. So we had a hand in the back, and then I'll take the hand from the front.
What kind of propulsion are we talking about for a Uranus visit? And is that something that's existing, or is there research going into it?
So the question is, what kind of propulsion do we need to get out to the Uranus system or the Neptune system? Do we have it? Conventional rocketry is fine. I mean, that's how Voyager got there.
Right.
It takes a long time, you know. That's why I said it takes 10 years, 15 years to get there with conventional rocketry. We don't want to go any faster. Like, there are people who's like, use light sails, you know, and then you go really fast. The problem is, we want to go into orbit.
Right.
And if you're going really fast, you have to slow down to get into orbit. So it makes more sense to use conventional rocketry, the kind of stuff we have right now, whether it's, you know, the SLS or, you know, it's Elon Musk's, you know, Starship, whatever it is, whatever it'll be 10 years from now. Those are fine. And then we just take enough fuel so that we can slow down, or we do aero capture when we get there. You know, there's a lot of possibilities. So we don't need to invent anything new.
This question here.
Yeah, if I remember correctly, one of the ice planets has a hexagonal feature at the poles. I'm not sure which one. Is it Neptune?
The question is, one of the giant planets has a hexagonal feature at the pole. That's Saturn. The polar hexagon of Saturn was discovered with Voyager, and then we've seen it since there. What this polar feature is, it's a wave pattern. Do you remember in my Uranus picture, the best ever, 2012, I showed you the waves in the equator? That was like an n=30 wave. There were 30 bumps and wiggles. There's a wave feature around the pole of Saturn that only has n=6. So if you could like peel it off and put it, it would do like 6 waves. And that's why it looks like a hexagon. Yeah, standing wave feature around that pole. We don't know if Uranus or Neptune has those, because we don't have the resolution to be able to pull out that level of detail yet. We need a mission. I want to go back.
Do we have questions from the sides?
I thought someone over here had one, no?
Okay, we have front row and then 3 rows back.
How do you differentiate a super Earth to a sub-Neptune?
Great question. The question is, how do you differentiate a super Earth from a sub-Neptune? That's all, I mean, that's a huge question. It has to do with the structure of the atmosphere relative to the interior. And so there's a gradation from, imagine an Earth that has a thicker and thicker and thicker atmosphere. That's one way to do it. So you have a solid body with a really thick atmosphere. On the other side, imagine the Neptune, where you have a huge thick atmosphere and a gradient down to a watery mantle. Those are kind of 2 end states, and where they transition is not well known. And so that's one reason we want to do these measurements of these. It's a complex field. I mean, you know, if I were an exoplanet specialist, I'd be showing you these plots of all this, you know, chemistry, and with this kind of chemistry, you would tend more towards the sub or super Earths, but with that type of chemistry, you'd go towards the Neptunes, and that has to do with the star that they're around. These are very complicated questions that don't have super simple answers, but it's a gradient. Sorry.
Okay, we'll take that question there and then see if there's one maybe from over here. There's one hand back there, and then we might be out of time.
So I was hoping you could shed some light on when we're deciding on what the next big mission should be. What are some of the factors we consider, and it's something that astrobiology on Mars take precedence over Neptune and Uranus.
Yeah, the question he's asking is, when we do our decadal surveys, how do we rank these missions? What are the criteria that go in there? You know, a lot of it has to do with what is considered really hot science. This question of astrobiology, can we find evidence that life existed on Mars? You know, is there water on Mars? You know, we've discovered water on Mars about 17 times, right? Just recently, it was you, it came to me, Mom, did you hear about this story that discovered ocean of water on Mars? And I'm like, what? And it's just like, you know, it's like water in the cracks of the rocks down deep. So, but just the idea that Mars may have at some time in its past been very wet and have conditions that life could evolve, that kind of trumps a lot of other science. And so that is why that rises up. Plus, it's a bandwagon. Like, we have so many missions to Mars. We have a huge community of people who study Mars. How many people do we have to Uranus and Neptune? Like, not many. So it's like, if you want to feed the community, you got to do where all, that's not entirely true. Once we sent Cassini to Saturn, all of a sudden people were coming out of the woodwork to do Cassini Saturn science. So, but really, it has to do with life. That's why Mars and Europa, people thought, oh, it's got an icy surface and an ocean underneath. Maybe there's life there. There was a paper that just came out like 3 days ago, was like, you know what, people, I don't think that they have the right conditions in the ocean in Europa to find life there. Maybe Enceladus is a better bet. So those are the kinds of things. Now, when I was running the decadal survey, the reason Uranus came up number 3 is I put together a chart and I said, science that is transformational, science that is incremental, or science that is like uninteresting. And I ranked the missions, whether it was transformational or just, or whether it was like incremental or, it doesn't address this question at all. We had good science questions and ranked the missions. And guess what? All the transformational science came from Uranus and Neptune because we didn't know anything about them. Anything you learned was fundamentally transformational. And so that's how Uranus popped up, and people are like, Uranus, the dark horse. And I'm like, it's the science, people. So anyway.
Okay, we'll take this one last question, and then we'll wrap it up.
I know that we made big investments, let's say, once every decade to send one big observatory out there. Have we considered making lots of really small investments and just flinging a bunch of instruments out there to see what it brings?
Yeah, a lot of people talk about that. We could talk about it for telescopes, but let's talk about it for Uranus and Neptune. Maybe we want to just make, a mission that will just measure the magnetic field of Neptune. That's all it does, right? And that would be great, but it would only do the one thing. And maybe we could also have I tell people, I want a mission to Neptune that just has a frickin' cell phone on it. Mm-hmm. Yeah. Just go out there and take some selfies and send them back. That would be transformational. But that's all it would do. It wouldn't answer any of the questions about the interior structure. We need an orbiter to do that. And so there's a big debate about whether or not, if you're only going to do something once every 50 years or 60 years, do you want to do like the one tiny thing and then have nothing else? Or do you want to try to push for the mission that will do the most science that it can, because that's your only shot for the next 60 years? So that's a debate we have. Now, telescopes is different. There's science that you require the large apertures to do. And you could have 50 tiny telescopes, and they're not going to do the science that's required with the large aperture. Exoplanets are like that. And people are, people are talking to us all the time. No, I can do it, with like a bunch of small telescopes. You can't, because they don't have the right filling factor. They will not give you the sensitivity that you need. So your question is a great question, and it's part of the debate that goes on in the community, the astrophysics community and the planetary science community. But my answer is, I worked on Voyager when I was a young person. We're coming up now on the 50th anniversary of the only mission ever to that world. And so I'm not content with sending just something that's going to just measure the magnetic field and take no pictures of those planets. I want to argue for the flagship mission that will do the comprehensive science. And the last thing I'll say is, another scientific reason you want the comprehensive mission is that to truly understand things, you need to measure them in different ways. You need to look at the magnetic field. You need to look at the gravitational moments from an orbiter to get the internal distribution. You need to see the atmosphere. And these things are all intertwined. They're a system. So if I take one measurement here and one measurement 20 years later and another measurement 30 years after that, I'm not going to be able to put it together into an integrated system and understand the planet and its system. That's why you want the integrated flagship class mission that would do all of that. So I will continue to advocate until I'm done for the flagship mission to Uranus or to Neptune. So thank you all.
Okay, great. Let's get going.